Welcome to the deep dive. I want you to just pause for a second. Wherever you are right now, walking, driving, sitting still, I need you to know that you are currently being, well, bombarded, not by sound, not by radiation, but by this invisible, silent swarm of particles. And they're rushing right through your body.
And when we say rushing through, we really mean it. They're passing through your skin, your bones, your organs, the chair you're on, the floor, the entire planet, actually, all without leaving a single trace. You feel nothing.
The numbers here. This is what's immediately just mind-bending. This isn't a few particles floating by. We're talking about a number that's hard to wrap your head around. Scientific estimates say that every single second, approximately 100 trillion of these tiny particles pass right through you.
100 trillion per second.
It's this incredible cosmic paradox, isn't it? We're swimming in this particle shower of unbelievable intensity, but we're completely unaware, untouched. So, our mission today is to do a deep dive into the science behind this. We're going to unpack the nature of these invisible visitors. Scientists call them neutrinos, but they have a much better nickname, the ghost particle.
A very fitting name.
We need to figure out what they are, why they're so elusive, and, maybe most importantly, why we should even care about tracking down something that's basically a cosmic phantom.
I love this topic because it forces us to zoom in and zoom out at the same time. To understand the neutrino, you have to connect the impossibly small, the subatomic world, to the vast, epic structure of the entire cosmos. It's particle physics meeting cosmic history.
Okay, let's start with the absolute basics then. If 100 trillion of these things are hitting me every second, what exactly is a neutrino?
So simply put, neutrinos are subatomic particles. They're in the same family as electrons, but the two things that really define their ghost-like nature are, one, they're much, much smaller than an electron, and two, and this is the big one, they carry no electrical charge.
Okay, that right there explains a lot, doesn't it? No electrical charge means they're not affected by the electromagnetic forces that, govern most of reality for us.
Precisely. They don't interact with the electrons in your atoms at all. They're fundamentally neutral. That's step one to being invisible.
Which brings up the next question. If they're everywhere, where are they all coming from? Are they just leftovers from the Big Bang?
Some of them are, but they are absolutely being manufactured right now. They're generated by some of the most powerful nuclear processes in the universe. The vast, vast majority of those 100 trillion hitting you right now, they come from our own sun.
The sun?
The fusion reactions happening at its core make it this absolute prodigious neutrino factory.
So every time hydrogen fuses into helium in the sun, it just spits out a neutrino.
That's it. And, we also generate them from nuclear reactions here on Earth, both natural ones and in our reactors. But the really spectacular ones, the ones that tell us about the history of the universe, they're born in these huge cosmic cataclysms, the massive explosions of giant stars, supernovas. Those are the real deep space messengers.
And that brings us right back to the central paradox. We know they're made by the trillions. They're passing through us constantly. So why are they so elusive? Why can't we feel this massive flow?
This is where we have to, get into one of the fundamental forces of nature. The reason you don't feel a thing comes down to how the neutrino interacts, or maybe more accurately, how it fails to interact with matter.
And the key principle here is something called the weak interaction.
Yes, the weak nuclear force. Neutrinos interact almost exclusively through this one force. And if you compare it to the others, gravity acts over huge distances. Electromagnetism is incredibly powerful. But the weak force is, well, it's exceptionally short range. It only works when particles get incredibly close, like basically crashing right into the nucleus of an atom.
And for a neutral particle like the neutrino, that almost never happens. It just sails right by.
It almost always sails right by.
I think we need an analogy here because almost never doesn't really do it justice. We need to get a sense of the scale of this.
That's fair. And the source material gives us one of the most extreme analogies in all of science. Imagine you wanted to stop a neutrino. You'd build a shield out of the densest thing you can think of. Let's say a solid barrier made of lead.
Right, lead, the stuff we use to block radiation.
Exactly. Now imagine that lead wall isn't just thick. It's impossibly thick. Not a foot, not a mile, but a lead barrier that is 1 full light year thick.
Hang on. 1 light year. That's the distance light travels in a year. That's nearly 6 trillion miles.
Yes. 6 trillion miles of solid lead. A neutrino could pass clean through that entire barrier, and the odds of it interacting even once are still astonishingly low. It just doesn't see the atoms in the shield.
Wow, that is the perfect way to picture it. If you can fly through a light year of solid lead, than a few inches of me or, the entire planet Earth,
Mm.
it's nothing. Zero resistance.
And that unbelievable transparency is exactly why scientists call them the ghost particles. They really are ethereal.
Okay, so let's get to the question our listeners are probably thinking. If 100 trillion of these are shooting through me every second, should I be worried? Is there any risk? Cellular damage.
It's a totally rational question, but no, you can relax. They're entirely harmless. Because they only interact via that weak force, they don't deposit any energy in your body. They don't cause any damage.
But the very thing that makes them hard to study is also what makes them safe.
Precisely. They are so indifferent to matter that, as the sources say, a neutrino passes through the entire Earth, as if the planet were just a sheet of transparent glass.
Okay, so this brings us to the next massive challenge. We have an invisible, neutral, superabundant particle that interacts with basically nothing. So how on earth do you hunt a ghost? How do we even know they exist?
This is where human ingenuity is just incredible. If you can't wait for them to stop, you have to build the biggest, most shielded, most patient traps you can possibly imagine, and you just hope for that 1 in a quadrillion lucky shot.
And these traps, I'm guessing, have to be far away from all other cosmic noise, all the other radiation hitting the Earth.
Exactly. So the main way we detect them is by building these massive detectors deep underground. We're talking miles down, in old mines and huge excavated caves. The rock itself acts as a shield.
And what's inside these giant underground chambers? What are they filled with?
The detectors themselves are basically giant tanks. I mean, some of the size of an apartment building. And they're filled with enormous quantities of ultra-pure water.
Water. That seems so simple for such high-level science.
It's cheap, it's stable, and it's full of targets. You need trillions upon trillions of hydrogen and oxygen atoms just to maximize the tiny, tiny chance of a collision. Because even with all that mass, the collision rate is just absurdly low.
What's the number again? How rare is this interaction they're waiting for?
We're talking about maybe 1 in a few million of the neutrinos that pass through the detector will actually hit a water molecule.
1 in a few quadrillion. So these scientists are sitting deep underground just waiting for this one cosmic lightning strike to happen.
That is the job. But when that incredibly rare collision finally happens, it produces this clear, unmistakable signature.
The ghost's fingerprint. What does it look like?
Okay, so when the neutrino slams into the nucleus of a water atom, it creates a secondary particle that's charged. And this particle is moving so fast, faster than the speed of light in water. It creates a kind of optical sonic boom, a faint, quick burst of light.
A sonic boom made of light.
Wow, exactly. It's known as Cherenkov light. It's this incredibly quick, lonely blue glow, the same kind of light you might see around the core of a nuclear reactor.
That's a powerful image. A single, faint blue flash deep underground in total darkness.
And that's it. That is the only way to see that a neutrino was there. They surround the tanks with thousands of supersensitive light detectors. And by tracking the shape of that flash, they could figure out exactly which direction the neutrino came from.
Which brings us to the big so what question. We've figured out they're everywhere, they're safe, they're nearly impossible to catch. Why dedicate so many resources to tracking a ghost? What's the benefit?
Oh, the benefits are. They're absolutely fundamental to cosmology. Precisely because they don't interact, neutrinos are the universe's pristine information carriers.
Right, they bypass all the cosmic dust and gas that blocks our view of everything else.
Exactly. Light gets scattered and absorbed, but neutrinos sail straight through everything. They give us this unfiltered, unclouded view into the past and into the mechanics of the cosmos. The sources highlight 4 huge areas where they're crucial.
Let's start with the sun. Why do we need neutrinos to study our own star? We can just look at it.
Well, the light you see from the sun today started its journey from the core tens of thousands of years ago. It has to bounce its way out. You're looking at old light. But neutrinos, they leave the core and get to us in about 8 minutes. So they give us a real-time health check on the sun's core.
That's incredible. We'd know almost instantly if something changed in the heart of the sun. What's number 2?
Understanding supernovas. When a giant star collapses and explodes, the core gets so dense that light is trapped inside for a while. But a massive burst of neutrinos escapes almost immediately, hours before we see the first light from the explosion.
So astronomers get an early warning system and a direct look inside the explosion itself.
A direct look. It tells us exactly how heavy elements are forged and then scattered across the universe.
And the third one gets into the really big questions, doesn't it? How matter originated after the Big Bang.
Yes, these particles are genuine relics. They carry information from a time when the universe was just seconds old. It was so hot and dense back then that light was trapped, but neutrinos were already free. So they preserve details from the very first moments.
They're like fossilized information.
That's a great way to put it. And that leads to the fourth, and maybe the most profound utility. They help us try to answer the ultimate question: why the universe exists at all, why there's more matter than antimatter.
It's truly awe-inspiring. These things are literally the oldest travelers around.
They really are. The sources are clear that neutrinos existed before the sun was even formed. And here's a final sort of beautiful and chilling thought about them. After the universe dies out, after all the stars are gone, the neutrinos, because they interact with so little, they may very well be the last thing still moving in the vast, cold darkness.
So we started with 100 trillion ghost particles passing through you every second. And we end with the idea that this invisible current holds the keys to our deepest cosmic past and maybe our ultimate future.
It's a profound thought, isn't it? It shows the universe is both terrifying in its scale and beautiful in its hidden mechanisms. We're just these tiny specks swimming in an ocean of secrets, constantly being pierced by information from the dawn of time.
It really is the ultimate humility check. And, the source material hints that this journey into extreme physics doesn't just end with the neutrino. We've talked about particles that move through everything, but the biggest mysteries might be the things we can't even begin to sense yet.
That's right. Finally, being able to trap the neutrino has kind of opened the door to even stranger ideas. I mean, if something this abundant is so hard to catch, what does that say about the truly invisible forces that make up most of the cosmos?
The sources hint at even more exotic stuff. There are stories about particles that might move almost faster than light. And of course, the biggest ghost of all, dark energy. The force that seems to be accelerating the expansion of everything. That might just be the next ghost we have to hunt.